Now it really turns out that the light sensor is not the only one that you might actually use. You can use something else as well. So if you hate light, let's go to sound. So now I do not know how to make a loudspeaker. So this is a loudspeaker that is playing whoever your favorite singer is, his song. Actually a buzzer. And remember, we cannot buy expensive speakers, so it's a cheap buzzer. And that's my robot. It has a microphone. And the microphone is tuned so as to pick up the frequency of this buzzer. So it hears sounds of that frequency. Now, unfortunately, what happens is, look at this formula again. I needed a vector to goal, and I needed a distance to goal. Now, distance to goal is proportional to the amplitude of the signal sound. So if I hear the music really loud, buzzer, if I hear the buzz really loud, I'm close by. If I hear just a faint sound, I'm far away. The problem over this thing is, just like light does not give you magnitude, so we had to use conic. The microphone does not give you the direction. And therefore, there are two things that you could do. One is that you can place in an array of microphones and then say which microphone records the loudest noise. And whichever microphone records the loudest noise, that's your direction. So direction is the microphone that records the loudest noise. Unfortunately, in light, the noises are extremely small. Where you are seeing is exactly where the light source is. However, in a microphone, the microphone picks up the signal along with a lot of noise, and because it picks up a lot of noise, what really happens is that the microphone that records the loudest signal is sometimes also that catches a lot of noise. There's some noise removal that you can do by all the signal processing techniques, but it's still a very delicate logic. There is another second logic that says that if you want to in any ways go with a single microphone, just travel a little bit in any direction. So you were at time t over here, and at time t plus delta you are over here, and this is what your buzzer is. So that's the sound signals going. Now, if here what will happen is that if you have travel sufficient, then you can say, is the signal getting louder or is the signal getting lower? If it's getting louder, then you're traveling in the same direction, then you go ahead. That's also, by the way, how some of you try to catch good Wi-Fi. Just keep on traveling. If that Wi-Fi level goes up and you just keep on traveling, which is actually another system. So that's your Wi-Fi, and this is your Wi-Fi antenna. So if the Wi-Fi signal is increasing, you are going towards goal. If the Wi-Fi signal is reducing, you are going away from the goal. And again, the Wi-Fi signal strength is the distance to goal. And the direction is based on this fact. You can actually, using three positions, try to approximately triangulate it up to know approximately where the goal is. That's the normal intuition that could be used in order to get the direction to the goal. And there's absolutely no reason why I should only use light, sound, or Wi-Fi. Any emitter transmitter can be used. And you know a lot of sensing, you know a lot of different types of waves, you know a lot of physics, so you know all the emitter transmitter pairs that are existing. So use anyone, and you know how much do they cost. How much does a light bulb cost? Pretty small. So these are what are the different ways I could potentially go into and try to kind of get towards the goal. Now, unfortunately, there is another behavior that I have to display, and that is obstacle avoidance. And again, you know, so let me not write down. So the repulsion from an obstacle O is a function of distance to obstacle, inverse cube, and direction to obstacle. Now I could use exactly the same sensors, but here is where I would like to reuse my last lecture. Remember, what did I say? They are cheap, they are budget robots, and I said practical artificial potential field. We actually use a LiDAR, but LiDAR is non-affordable to many people, so they use a sonar ring. And I told you every sonar is at a distance alpha. So the distance is 2 pi by number of sonars. Starting from 0, the first one is always at 0. So if you have got 4, it is 0, 90, 180, 360, 240, 270, and similarly for the others. So, and then this really tells you what is the distance to obstacle. So I don't repeat that. This only gives you distance to obstacle, this gives you the angle to obstacle, and all the calculations are already done in potential field. So my sensors are, to write it more clearly, either a sonar, which is sound navigation and ranging, or ultrasonics. Sonar is a low distance sensor. That's what we use in indoor robots. Ultrasonic is higher frequency, and that's the one that self-driving cars use, so that you don't. In fact, why self-driving cars? If you have a lot of automated features already in the cars that you drive, adaptive cruise control, sometimes for parking as well, it actually uses ultrasonics to get distance from the obstacles. And both these sensors are actually low cost. Surprisingly, the most expensive sensors in self-driving cars is not ultrasonics. So that's the one. Now, of course, there's another sensor that I talked about. That's the bump sensor. Let's have one. And that's the most primitive obstacle avoidance. So from above, you know the angle to the affinity towards goal. All your this thing is, you go towards goal, you have no way to find out where the obstacles are. You collide with something. So take this robot over here. It has a bump sensor. So it goes over here. That's the goal. It approximately goes over here, but there's also an obstacle. It collides. So it turns around as much as it can get from its encoders, or it notes its angular speed, so it shows angular speed so as to approximately turn around. Then it travels a random distance, and then it again invokes the attraction towards a goal. It again bumps, then it again turns around, goes into a new direction randomly, and then it again invokes the attraction towards the goal. It again bumps. So whenever the collision with the obstacle happens, this bump sensor, which is just a switch. So when you collide with an obstacle, the switch gets activated, then you again go random. So it's actually not used. The robots use bump sensors just for finding out that yes, a collision has happened. I'm not sure what you can do after that. Of course, you can do a lot after that. You need to switch off the motors because collision has happened. Sometimes you need to call for human help. I've collided. So the bump sensor actually lets the robot know that a collision has happened. Some motion planning algorithm, some navigation algorithm theoretically do use bump sensor for all these kinds of things, but right now we're dealing with swarm, so we need to go with budgetary sensors which are bump. And now what we do is, there's also a tactile sensor. So if it's tactile, then it can actually also tell you how close it is. But then tactile sensors and bump sensor, for a binary tactile and a bump sensor, are nearly the same thing. So with this we come quickly to communication. The robots could use communication via Wi-Fi. It was very expensive when we installed it in the hostels for different reasons, but you can actually buy a Wi-Fi router. You can afford that much. The good thing is you don't have to replicate it with thousands. They could connect via Bluetooth. You know, it's very cheap. You could also do Zigbee or whatever. Now, what really the thing is that these are many robots, and each robot has a range. So this robot has this range, and therefore this robot really communicates through this using its transmitter, using its Bluetooth transmitter receiver, Wi-Fi transmitter receiver, Zigbee transmitter receiver, and that's a network that gets formed. This can also communicate to this. And this is called as a wireless ad hoc network. The most popular course in Triple IT Allahabad. So that's a wireless ad hoc network. I need not say it's wireless because these blue are not the physical connections. It's ad hoc because the robots will move and this network will change. So it's actually a mobile wireless ad hoc network. It's ad hoc because if the robots go away, the connections will break. If they come closer, new connections will get formed. And that's what happens as a communication between all the different robots that you have over here. Some of them might actually get disconnected, like one robot may be very far away, and in that case, the problem is it has absolutely no idea, so it'll have to travel randomly until it accidentally comes into a communication range of at least one robot. Then it's connected to the same wireless ad hoc network, which means it can be a part of whatever team sport that these robots are playing. Now, we looked at attraction from the goal. We looked at repulsion, so that means my artificial potential field can be implemented, and thereafter now whenever I use the term artificial potential field, I'll say you know how to do that. I'll not tell you. So now let's go on into a little change in the sensors, and again that I'm going in a little change in sensors, so let me first tell you why am I doing that. So I have robots of two types, the reds and the blues, and it's social potential field. So in social potential field, we said group 1, group 2, these are group 1, group 2, and we want them to say cluster out. So from our understanding of social potential field, what we know is that in terms of social potential field, this means the red and blue repel, the red attract, the blue attract, and the blue red repel. By doing this, whatever will happen, I'll care about it later. That's when I start discussing the behavior, but that's broadly what I want to see as my behavior. That's what I want to implement, this kind of attraction or repulsion. Now the thing is that luckily there's no attraction to goal. Even if there was there, we know how to do it. So we would have taken a green colored light and everybody would have, using my own omnidirectional camera, did some color filtering, detected this is where green is, and then went towards the green. That's simple. And everybody can do repulsion from everyone. So repulsion is not a problem. The problem is differentiating between this and this. So if it's blue, I should repel. If it's red, I should attract. And by now, we have absolutely no means to do that. So let me just draw in two robots over here. One which is blue and the other one which is red. And let me tell you what is that I'll do very interesting. So for the blue robot, I take blue LEDs. Now the difference between the light bulb that you're using at home and LEDs is the LEDs will go in a single direction. So I'll need lots of them. And I take red LEDs here. So unless you're in the line of sight, you'll actually not be able to detect it. And this is blue LEDs. Now your LED television is expensive for different reasons. It's not expensive because of LED, I am very sure about it. If you want to find out why your LED television is expensive, count the number of LEDs. Fun exercise. And think about the resolution. So that's the light emitting diodes. They transmit light of the color. You get lots of color options when you go to LEDs, and they are so cheap that many electronic students purchase them from their own pocket money given by their parents. And what of course I also have is the same omnidirectional color transmitter. And to make things simple, let me say that this blue one is being planned, and let's have another blue one over here. So what this blue screen will say do is that in this direction it will see a red dot from this LED, and here it will see a blue dot from this LED. This height is artificially created because it will be detected at exactly the same height. So I had to do that, otherwise the diagram would have been clear. And therefore you know that you need to apply a repulsion here due to the red robot, and you need to apply a attraction here due to the blue robot. But then if you apply this attraction to the blue robot, the two robots will collide. Attraction, 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 there, collide. So you also place in Ultrasonics, sonar. So what really happens is that if they are far away, the constant force applied by the The constant force applied by the LED detectors is high, it's constant, and therefore it's high. There's no repulsion because sonars don't sense far off obstacles, but when they come very close to each other, the sonars suddenly become very active, and repulsion from obstacle is very sensitive. So the moment the distance reduces below a threshold, the sonar sensors are like the distance are very small. They're actually at the edge of all the sensors are actually at the edge of the robot boundary as closely as you can place them. And the sonar sensors are like, it's not good to move in this direction. Now, actually, with real robots, we are very careful it doesn't collide because it has at least a very good looking body and we don't want to make it look dented, just like your car. But then with these swarm robots, even if they collide, it's not that we care too much. But then sonars are there to help. The sonars warn when the distance is too small. 1 upon dq becomes too large, and the force becomes so large that the attraction from LED is too small in contrast to that. So let me write down the rules here. So the robot will feel attraction towards the goal. In this case, there is none. For all the blue spots detected, so this image will take multiple blue spots. So for all the blue spots detected, it will feel an attraction. For all the red spots detected, it will feel a repulsion. And from all the sonar sensors, it will feel a repulsion. Previously, I was actually summating across agents, but that requires image processing. You need to see the person and stuff like that. Now I'm directly summing across whatever my sensors are reporting. So summation over all the red spots detected, summation over all the blue spots detected, summation over all the sonar values detected. That is F total. If you want, of course, you can, instead of LEDs, I can use sound as well. So every robot has a buzzer, omnidirectional buzzer. So you only need one of them. And every robot also has microphone. Now, in order to differentiate between robot, so I say every group has a different song being played. Of course, it has a different frequency of sound. So you're one type of robots, you follow everybody who's playing hot Punjabi music, and the other group is the one that has nice vintage English songs. Frequencies are different. One is playing at some hertz, the other one is playing at some hertz. You know, noise filtering, like I did not talk about color detection over here, simple color filter. So just like that, you have frequency detection or frequency filters, which will tell you where to go, or you could use any one of them as well. And that's how you can differentiate between the different type of robots for the implementation of a social potential field as well. If you just want robots to attract each other, all of them, leave the red and you have whatever it takes around over here.